Hey there, in this lecture I am going to describe how you can derive a relativistic version of Schrodinger's wave equation for gravity. Um, so one of the things that PySpace does is it has a relativistic version of the the velocity, the kinetic energy formula, and the potential energy formulas. Um, if you've been following the theory, you'll know that there's an advanced formulas document, and in the advanced formulas document, I derive the kinetic energy relationship to the potential energy relationship, and I have explained in the advanced PySpace formulas PDF or HTML file that you can set the potential energy equals to the kinetic energy. In this case, this is the potential energy, and this is the kinetic energy. The nice thing about PySpace is that these formulas, in a very kind of logical way, tie in with quantum mechanics, in that you can represent the velocity increase as a shrinkage in the size of a sphere or an atom, what I call a pi shell, and you can map that quite easily to Euler's identity. I'll do a different chat about that, but just for the moment, just pay attention to this relationship. Potential energy is kinetic energy. This is the same thing that Newton did, except that he did mgh over here, and he did half mv squared here. Now, I've shown in previous lectures that you can derive all sorts of interesting values out of this. You can calculate the the escape velocity for various planets. I've shown how they tie up. I've shown how you can calculate kinetic energy with this value and how it ties in with the Newtonian result. And then I've put it up to a large value up near the speed of light. And the nice thing about that is that it returns a value in area terms, which is a c squared result, and it returns a result no larger than E is equal to mc squared. So this equation here, when you pass in the speed of light, gives you E is equal to mc squared. This is also limited by c squared. G times h can be no greater than c squared. I've shown how you can also apply these formulas in the advanced PySpace formulas to black holes and calculating the distance one travels to achieve a certain velocity and so on. So these are well tested formulas in the advanced PySpace formulas PDF, if you're not familiar with them. So let's take this kinetic energy equals potential energy formula, and let's apply it to Schrodinger's wave equation now. Now this is Schrodinger's wave equation. He developed this when he was in Austria, if I recall correctly. So when he originally tried to develop the formula, he wanted a relativistic version of it, but he came up with this version. He wasn't very happy with it, apparently, and he was almost not going to publish it, but he did. And lucky for everybody, he did, because this is probably the most foundational formula in quantum mechanics, and probably in all of physics, in modern physics. It's used to calculate the probability of an electron inside an atom, a hydrogen atom initially, and other atoms, you based on the quantum numbers and based on the wave function. So let's break this formula down into its logical components as opposed to its mathematical components. And then what we'll do is we'll map it back to the PySpace equivalent of it, and it's actually surprisingly straightforward if you understand the logic of the formula as opposed to the mathematics of the formula. So I'm going to just go up here a little bit. The formula is based on what's called the Hamiltonian, and the Hamiltonian is actually a really simple idea. It's foundational in quantum mechanics, but it's essentially the combination of the kinetic energy. That should probably not be He, but just H, but for the purpose of this document I did He, so just think Hamiltonian there. It's quite straightforward. What Hamilton did, he was an Irish math scholar from Trinity College. What he did was he summed up. He said the total energy of a system is its kinetic energy and its potential energy, which is here. And what Schrodinger did was he realized, or he made the intuitive leap of saying, well, if the total energy of a system is its kinetic energy and its potential energy, and we know the wave amplitude, then it must be the kinetic energy and potential energy times the wave amplitude. That was basically what he formulated, and then you get a negative value for the kinetic energy relative to the potential energy, because the sum of those two values equals 0. So you can represent this very fundamental formula in quantum mechanics as just adding up the kinetic energy and the potential energy of a system times the wave amplitude. And he came up with, he used for the wave function, he used this other very smart approach. He used the exponent function with the imaginary axis. That's this part here. I'll talk about this piece next. So this is the this symbol here is just the wave function with respect to time. So what you're looking at here is a formula that talks about the rate of change of a system in terms of its energy with respect to time, and we know the what we do is we have the kinetic energy component, the potential energy component, and the wave function component, which is the quantum mechanical view of things. And we have h bar, which is the smallest. In the way to describe that in PySpace is it's the smallest possible diameter divided by the circumference. So it's kind of like a unit energy calculation for the smallest part of a wave. So let's take a very quick look at the wave function. If I pop up here, this is the quantum document I'm looking at. Let's just go here. So this is a rudimentary version of Euler's identity, and all it really is it's a circle, which is a bit like PySpace. Up here we have the imaginary axis. This is the real axis, which is the cos axis, and then the sine axis. So in quantum mechanics, they have this concept of the imaginary axis. The way I describe that in PySpace is I call that an unbound wave function. In other lectures I'll try and explain in more detail what that means. But it just really means that entanglement in quantum mechanics is not just, without getting off the point, entanglement is everywhere in quantum mechanics. It's not just these examples that are just shown with the spin up and the spin down on the electron. According to the PySpace theory, and everything is entangled. But let's just focus on the formula that Schrodinger derived. And so he used this form here for the wave function, and he altered the inputs here based on the situation they were modeling, and then that value gets multiplied by another value, which in our case is a kinetic and a potential energy component. So let's go back to the example formula that Schrodinger derived. So it's really simple. It looks complicated, but it's really simple. This is the kinetic energy component here. This here is the h bar squared over 2m. That's like that's kind of like the quantum version of a half mv squared. And this v here is the potential. And both of them are times the wave amplitude, the wave function, which is modeled on an exponent function with an imaginary axis. And that's it. It's really straightforward. What Schrodinger did was he then solved this for a hydrogen atom, and he produced these fields, probability fields for the potential position of an electron, and that's it. That's what he did. It's probably one of the smartest functions in physics, physics at the moment. It's kind of, you can derive everything from it, and the reason you can derive everything from it is because it has the wave function, which is the quantum view of things, and it has the particle part, which is the potential part. So let's just take a look at the potential and the kinetic part. So we're dealing here with a model. We're dealing here with an atom. So this is the thing about quantum mechanics at the moment is it's all about the small stuff, or the tiny stuff. So this potential is actually modeled after the electric field potential. So the electron is inside it's inside an atom which has an electric potential, and that gets calculated. And we know that from the very elementary physics that the electric field is very like a gravitational field. So this is the first point to make. So we're dealing with a potential that's like a gravitational field. In terms of the mathematics, it's a squared function over, or it's a value divided by the distance from the center squared. And this is the modeling the smallest possible diameter, which is h bar over squared over 2m. So from this formula, we can derive the Schrodinger wave equation for the possibility of an electron appearing at a point within an electron. Now let's just take this concept and apply it to a gravitational field. So let's take a look at that idea. So what we have here now is the pi space equivalent formula for a gravity field, and it's pretty simple. When you have a kinetic energy in pi space, if you follow the theory, one of the fundamental things you learn is if you move down inside a gravity field, you increase velocity, but your diameter shrinks. If you move up, it gets larger. So as you move down, it shrinks, which is this part here, the kinetic energy part. We're dealing with wave amplitude. In a previous lecture, I've described that the wave amplitude that quantum mechanics uses, this is the next intuitive step, is it maps to the diameter of the actual observable. So the standard units are 1. So typically when you're working in quantum mechanics, you talk about the wave function returning an amplitude of 1. So in this case here, it's 1, and here is 1. and how do you make a particle larger than that? And the answer is pretty simple. You need to know its position within the potential. So in the case of an electron, when the further out it is from the further out it is, the larger it is, and that changes the wave function. So it's no different here. The further out that you go from the gravity field, G times H. G is the area change with respect to distance, so you multiply it by distance. The units are area change. In pi space we map area change to the diameter squared, the maximum diameter c, so it's GH over c squared. This is a little bit like general relativity. Sometimes in some of the books I've read, they have G over 3c squared. That's not the way you do it in pi space. In pi space, it's G over c squared, and the reason is that what they do is they divide each axis by 3. There's 3 axes, so they divide by 3. But you don't need to do that in pi space, because the assumption is that that it's the diameter of the sphere which changes. So if you apply to one diameter, it's a geometric progression, so you don't need to. So you just divide GH by c squared. So that's the potential. So that's, just think of that as the object getting larger in gravity as you move it up, okay? And then if you move down at a speed, then within a gravity field, or even if you have a constant rate of acceleration, it's this 1 minus the cos of arc sine v over c. So that's the shortening. That's why it's a minus. That's a shortening of the diameter. The wave function gives you the initial amplitude, which is squared. Complex conjugate squared forms the diameter. So the amplitude maps to the diameter, and then GH over c squared makes the diameter larger, and this makes the diameter smaller. And then we just do some elementary reorganizing of the values. We get rid of the minus here, and then what we do then is we multiply both parts by the wave function, and then we get this version of it, and then we get the final result, which is really nice, and I think so anyway, is that we have the Planck's constant, we have the modified Planck's constant, which is the Dirac one, we have the wave function here, which is quantum mechanics, we have the classical mass concept, we have velocity, which is Newtonian, but the cos arc sine makes it relativistic, so that's special relativity. So this part here back is special relativity, and then this is you could argue this is general relativity. So it's got general relativity, special relativity, it's got the quantum mechanics, and what's nice is that you have a quantum mechanical formula for the big stuff, you know, like the planet or the planets, and you can imagine in a gravity field that just like in an atom, that the gravity field is like a standing wave. It's a similar approach. Now the difference is that if you're running an experiment in a lab and you have the slits, right, and you're under gravity, and you know the distance you are from gravity, and you know how much velocity there is, and you can model the wave function for the planet, you have to take into account, and this is the meat and potatoes of this formula, you have to take into account all the objects in the lab. It's like you cannot just assume that the wave function is a standing wave. The minute that you put an object in one part of that room, it affects the wave function. So we move into an understanding of quantum mechanics where the room is altering the wave function, right? Now in an atom there isn't so much in there. You have the quantum numbers, but in a room you can have objects of different mass, of different size, of different position. So that's what you've got to work out for this formula. It's brand new, and I need to just work a bit on it more. But this is how you can derive a Schrodinger type equation for our world, and you can see if you travel at the speed of light, the cos arc sine part cancels, and you're left with just the wave function. And you can see, depending on your height, you can see that you increase the wave function, or the size of the diameter of the wave function, or the amplitude, I should say. And that's it. That's the formula. So these building blocks have all been fairly well tested. The building blocks being these two guys here. Hang on, these two guys. They've been fairly well stress tested in the advanced PySpace formulas document. That's a PDF, and it's available on the website, the storytwig.com, PySpace, the PySpace theory on storytwig.com. I also have it up on archive.org if you're interested. But so that's the idea. Really simple. You have a relativistic version of kinetic and potential energy, but they also are compatible with. The important thing is they're compatible with Euler's identity, and the key thing to the formula is that Euler's identity is not just for quantum mechanics; it's also compatible with PySpace. All right, that's it for now.